flux is pretty cool. It's just the integral of some flowing thing, something that's moving and flowing, some flowing thing, which is a vector, dotted with dA, which is normal to the surface that we're finding the flux through. So let's say we had some net. This net has a very particular job. Its job is to catch flux. This is a flux catcher, I guess you can call it. This net catches flux. And let's submerge it in water right now. So it is underwater, and right now it's in still water. The water is not moving. So right now, the water is not moving. There's no flowing thing, so the flux through it must be 0. There's no flux going out of it, no flux going into it. The flux is 0, because this is 0. But what if now we gave the water some current? We gave it some velocity, v. Now the water is moving. And it looks like this. And let's say we trap some water inside of our net. So we close our net, we close our thing that catches flux, and we have water inside, and it's moving with this current. So there would be some flowing vectors coming out of the net, like so. And, well, we know that flux is just, we're adding up, we're summing up all those vectors dotted with their dAs. So if we look at each point, the dA to this surface, right over here, looks like this. This is the normal vector, so dA is in that direction, so there's some dot product over here. But over here, it goes this way, and they're practically 90 degrees apart, so this dot product is going to be close to 0. And over here, the vectors are in very close, very similar directions, so the dot product is almost going to be the normal vector and the flowing thing dotted together. So we have to sum up all these different dot products, all these different flowing things dotted with dA, and we're going to integrate them and add them up all together to get the total flux. So let's just say that our net, for some reason, is made out of clay, which means we can mold it and bend it and change it into whatever shape we want. We can make it as big as we want or as small as we want, but it's made out of clay. This net is made out of clay because it lets us change the shape of it. So what does this all have to do with electricity? Well, one thing in electricity that could be the flowing thing, in this case, is the electric field E. So let's take a point charge, for example. Here's a point charge. It's positive Q. And let's look at its electric field. It must be extending radially outward from the point charge because it's originating at the point charge because the point charge is positive. And now let's take our net that's made out of clay and let's put it into a specific shape. Let's take it like this, and we're going to make it look like this for some reason. Just like that. So this is what our net looks like. There we go. So now what would our flux be coming out of this net? These are our flowing vectors. In this case, it's the electric field. This was a velocity vector. Now it's an E vector. So let's look at our normal vectors. Let's look at our dot products. Over here, they're in just about the same direction. So the dot product would be E times dA. Over here, they're in pretty different directions. Over here, they're also in quite different directions. Over here, they're actually quite similar. So again, all these dot products are different all around our surface. They depend on whatever angle the electric field vector is coming out of this surface in relation to the normal vector, and to the normal area vector. So this guy Gauss came along, and he said something pretty remarkable. He just said that this is equal to Q enclosed, whatever charge is enclosed by our net, divided by epsilon naught, the permittivity of free space. And this is such a simple yet such a remarkable statement because it's so powerful in its simplicity. So let's take our point charge. Let's just move it over here for a second. Let's move it over here, and let's redraw its electric field. And now let's try to make this a bit different. What if we didn't want to add up infinite dot products? What if we wanted to make things a bit more simple? Well, it looks like this electric field is spherically symmetric coming out of this point charge. So what if I just made my surface a sphere? What if I took my net and I made it into a sphere, like this? And it enclosed my charge in the middle, just like that. So now, let's look at our normal vectors. Over here, here, it looks like they're actually all pointing in exactly the same direction as the electric field at that point, which means all the dot products at this point are just E times dA. They're all the same. And so now if we look at this equation for flux, we see our flowing thing is E. So the double integral of E dotted with dA. Well, these dot products are just the same all over our surface. So we can just pull E out of the integral because it's the same everywhere. So this just becomes E times the integral of dA over our surface. And, well, this is just A. So we just have EA. And let's look back at this equality. Remember, we have this equality. So EA is equal to Q enclosed over epsilon naught. And A, well, my surface, my net, I made into the shape of a sphere. So A is just 4 pi r squared. So we can solve for E and get that E is equal to Q over 4 pi epsilon naught r squared. And that's just KQ over r squared, which is the electric field of a point charge. So we were just able to find the electric field of a point charge using Gauss's law. So Gauss's law is not supposed to make things more complicated. It's not supposed to make things more complex. Gauss's law actually simplifies everything. It's a tool that we can use to our advantage, at our disposal, to easily solve for the magnitude of the electric field of a point charge or a distribution or whatever we might have. So we're taking this net we have that catches flux, which is, this net is formally just called a Gaussian surface, and we're putting it into some shape. We're looking at the electric field, and we're going to take our net and put it into some shape that makes this integral very convenient and very simple so that we can take E and pull it out. We're using our Gaussian surface. A Gaussian surface is not a real thing. It's an imaginary thing that we make up, that we create. We can make it into whatever shape we want. In this case, I made it into a sphere. In this case, I made it into some weird shape that makes our integral not so nice where we can't pull out E. But the whole point is that we're taking our imaginary Gaussian surface, it's a mathematical surface, and we make it into whatever shape we desire so that E can come out of this integral. We can have E times A and easily solve for E using Gauss's law. So Gauss's law really does simplify things for us. It's a tool that we can use to our advantage. And in the future, another example of something we might see in the future, maybe we'll see a line of charge. Let's just say its field goes like this. It's a positive line of charge. So this is just another example of how we can use Gauss's law. So we have this field. And how can we get the magnitude of the field using Gauss's law, using our net, our Gaussian surface? Well, let's see. How can we make our shape into something convenient and easy? Well, you might try at first. Maybe you might try making it into a bowl-like shape, like this. Maybe for some reason we think that this could help us. Let's see if it does. So let's look at our normal vectors. Oh. Over here, they are actually over here, they are nearly in the same direction. Over here, they're in slightly different directions. So again, the dot products are not the same everywhere. This integral then does not become simplified. So this isn't the best Gaussian surface we can use. We can still use it if we want to. We just have a very complicated integral, which won't be so useful for us. But what if maybe, let's say we had spherical caps like this. So we actually, circular caps. And we had a cylinder as our Gaussian surface. We turned our net into this thing. Now let's look at our normal vectors. So over here, it looks like they're actually all in the same direction as our electric field vectors. Same thing on this side. They're all in the same direction as the electric field. So this makes things easy. Again, we can pull E out of this double integral, and we'd have EA is equal to Q enclosed over epsilon naught. And Q enclosed is going to depend on whatever surface density or linear density we have of this line of charge, and then we can multiply it by how much charge is actually enclosed over here by our Gaussian surface. Well, we can multiply it by some area or some distance to get that charge enclosed, and then we can also end up solving for E. And in this case, we actually have two sides that the flux is coming out of. We have flux coming out over here, and we have flux coming out over here. So this would be 2EA is equal to the charge enclosed over epsilon naught. And that was just a very brief conceptual introduction to Gauss's law. If you think of it in terms of this net that you have that you can change into whatever shape you want, this Gaussian surface that you can make into something that makes life easier for you, then Gauss's law is really just a great tool that we can use to our advantage to solve for the electric field.